Hi, in this video I'm going to introduce the concept of a basis for a vector space. Now a basis is a set of linearly independent vectors which span the space. I've done a previous video on linear dependence, so I suggest you watch that if you haven't already done so. What do we mean by spanning the space? Well, a spanning set is a set of vectors which all other vectors in the space can be represented as a linear combination of those vectors. And we've got another idea of the dimension of a vector space, which is denoted by dim and then the name of the vector space, and that's the number of elements in our bases. So for example, the simplest basis in R3 is what we call the standard bases, where we have three vectors E1, E2 and E3. E1 is 1, 0, 0, so this you can see points along the direction of the x-axis. E2 is 0, 1, 0, which points along the direction of the y-axis, and similar for E3 with the z-axis. Okay, so you might know these are also known as I, J, K, and this is the standard basis. It's the simplest basis for R3. Okay, so here's an example. Here we've got a set of vectors W. We need to show that the W is a basis for R3. That means we need to show that these three vectors are linearly independent. Okay, so we form an augmented matrix with the columns of the matrix to the left of the partition are our vectors in W, and we're going to row reduce to reduce row echelon form using Gauss-Jordan elimination. Okay, so going through the steps, we eventually get down to the reduced row echelon form, and if we can see we had the identity matrix to the left of the partition, which means that this W is a linearly independent set of vectors, and therefore W is also a basis for R3. Okay, so why do we need to have different bases? So if we've got the standard bases in R3, that's the simplest. Why would we ever need it different? Well, there are several applications, but we also need to consider how we represent a vector with respect to a different basis. So here I've got an xy to R2, and I've got a point in R2 with coordinates U1 and U2. Now what does these coordinates actually mean? Well, if we have the standard bases, E1 points along the x-axis, E2 along the y-axis, the coordinates U1 and U2 is how much am I multiplying my basis vector E1 by to get to this point, plus how much am I multiplying my basis vector E2 to get to this point. So U1 times E1 plus U2 times E2 gets me to my point. So U1 and U2 are actually what we're multiplying our basis vectors by. So when you think about coordinates, you're actually thinking about what are we multiplying our basis vectors by to give us to this position. Okay, so that's the linear combination U1 plus E1, U1 times E1 plus U2 times E2. Now what happens if we've got a different basis? So here I've got a basis which is V1 and V2, and I want to represent the same point with respect to this basis. So what I would do is I'd multiply V1 by some scalar, let's call it W1, and I'd add to that V2 multiplied by another scalar, let's call it W2. Now this will get me to the same point. So this same point can also be represented by W1 times V1 plus W2 times V2. Okay, so you can see on the left hand side of this equation, that's represented with respect to the standard bases E1 and E2, and the right hand side is the same point represented with respect to V1 and V2. So a change of bases is how do we go, for example, from the standard bases to a different basis. So I'm going to show you by example. So here we've got the vector 4, minus 2, 3. I want to represent this vector with respect to this basis W. Okay, so what I need to do is we need to solve what am I multiplying the first basis vector by, i.e. W1, plus W2, which I'm multiplying the second basis vector by, and similar for the third. I need these to be equal to our vector 4 minus 2, 3. So I need to solve for W1, W2 and W3. So this is a linear system, and I could write this as a matrix equation. Okay, so notice that this coefficient matrix are the columns of the coefficient matrix are our basis vectors, and we're solving for W1, W2 and W3. Now, before, in the past, I've solved this using Gaussian elimination, but what I'm going to do here is invert this matrix and then multiply it by our vector. Okay, so the inverse of this coefficient matrix, so you can calculate this using the adjoint determinant formula or using Gauss-Jordan elimination, but this gives us the inverse, and therefore I can multiply the inverse by our vector to calculate this is a vector 4 minus 2, 3. On the right hand side, this 1, 3, 0 is this vector represented using the basis W. Okay. Now, why did I choose to invert instead of solve using Gaussian elimination? Well, if I had a different vector, so let's say I had a different vector than 4 minus 2, 3, I can use this matrix to simply multiply another vector to give us our vector with respect to a different basis. So that's known as the change of bases matrix. Okay, so I can represent any vector in R3 with respect to our basis W by multiplying by this change of bases matrix.